Okay, guys, this is section 6.3. I think it might say 5.3 on your paper. For whatever reason, I kept going back and forth between 6 and 5, and I thought that it was different in the new book, and it's not. And whatever, we'll figure it out. It's actually section 6.3. Volumes by cylindrical shells. So, if you guys remember from Calc AB and BC, that there was a way to take something which was revolved around an axis, a function which is being revolved around an axis, and find its volume. Typically, we would do that by slicing it, getting a whole bunch of either circles or washers, so disks or washer method. There's a different way to do this, and the reason that we have this different way is because some functions that we're given are going to be really difficult to do by standard disk and washer method. So that's what we're going to talk about. It's this method of cylindrical shells. All right, so let's go ahead and excuse me, examine a function where this might be the case. So we have the area bounded between the curves y equals 2x squared minus x cubed and y equals 0. So let's go ahead and do a sketch of what that looks like over here. All right, y equals 2x squared minus x cubed. If you went ahead and put this into your calculator, it's going to look something like this. Let's extend that out there. It'll look something similar to that. It's probably not perfect, but it's going to look similar to that. So if I'm bounding this thing by that curve in y equals 0, of course, being the x-axis. So here's our bound. And then let's see if I can trace this in blue. Probably should have just drawn it in blue in the first place. There's something like that. That is the area that we're going to try and revolve and try and figure out what the volume would be. So if we were going to revolve this thing specifically around the y-axis, so if we're going to revolve it around the y-axis, it's going to go around there somewhere, right? In this case, it's already solved for y. Both equations are solved for y. This would be really easy to do if we were rotating it around the x-axis, around the horizontal axis, because every slice would only go up to the function y equals 2x squared minus x cubed. The problem is, if we're trying to do this where we revolve this thing around the y-axis, what you should see here is, if you remember the idea of a disk and a washer, you needed an outside radius and an inside radius, because if you revolve this thing around the y-axis, it is going to create something that has a hole in the middle. So what we would need is the inside radius, and we would need the outside radius. All right, actually, let's use capital R for that, for the outside. The problem with this is, one, it's the same function. The inside radius and the outside radius actually attach itself to the same function. That makes it more challenging to do. Splitting this thing up into two different things would be very difficult, and looking at the equation y equals 2x squared minus x cubed, that's not easy to solve algebraically for x. Okay, that would be very, very challenging to do. So, because you'd have to solve a cubic. So, in order to do this, we came up with another way of figuring this out. Again, if they told you that this thing was revolved around the x-axis, this would be easy. You'd just go with your standard, actually there wouldn't be a hole in it at all. You'd just go with your standard disk method. You revolve it, integrate from the left to the right, and you'd be good to go. In our case, revolving it around the y-axis is going to create a problem. So this is what we're going to talk about. All right, so how can we make the process a little bit more convenient to do? So what we're going to look at here is one cylindrical shell. And it's called a shell specifically because it's not a solid cylinder. It's basically a cylinder with a cylinder cut out of the middle. If you can kind of see that you basically have what we would call a shell of a cylinder. One of the things that we're going to need is we're going to need to be able to figure out what the volume of a cylinder is. Hopefully you guys remember this, but if not, this is the equation for the volume of a cylinder. It's pi r squared h, which is basically the bottom, which is pi. The bottom, which is a circle, which is pi r squared, and then times a height of some kind. So it's basically stacking a bunch of circles infinitely on top of each other to create a volume. All right, so this one in particular, like I said, you can hopefully clearly see that there's a cylinder here with kind of a cylinder cut out of the center. So you basically hollowed it out, which is why we call it a shell. So if I wanted to find the volume of this in particular piece, which is over here on the left-hand side, what you would have to do to find the volume of the shell, what we would have to do is we would have to find the volume of the entire thing as if the inside was not cut out. So that would be the volume of the outer piece. And then we'd have to take away the volume of the inside piece, so the piece that was hollowed out of there, and that would give us the volume of the shell which is left over. Okay, so we can actually do an equation here to help figure this out. And we're going to kind of come up with the actual equation that's going to help us with this. So I'm going to try and keep the picture up there on the screen while I do this. All right, so the volume. Remember that volume is pi r squared h, so I'm going to take pi r squared 2. As you can see here, the outer radius goes all the way to the outside, so that's your r for the outside piece, times its height, which is going to be the same for both of them, minus pi r squared of the inside one, which is a 1, or sub 1. There's the inside radius right there, and then times h. All right, so using a little bit of algebra, we can factor out the pi. We can also factor out the h, but I'm going to put the h on the outside on the right-hand side. And what I have left over is r2 squared minus r1 squared. What you should see there is that I have a difference of squares inside of there and a difference of squares factors. So what we're going to get is that the volume is pi r2 minus r1, r2 plus r1, h. Okay? This is where you kind of have to be like, okay, where did they come up with this part of it? Well, remember that if I do something to this equation, and I'll scroll back up to that if we need it. If I do something to this equation, basically I have to keep the balance. So what I'm going to do is I'm actually going to multiply the entire right side by 2. And you might say to yourself, okay, that means I have to multiply the left side by 2. That is correct. But instead of multiplying the left by 2, I'm actually going to go ahead and divide the right side by 2. And you're like, what's the point of that? Just hang on with me, you'll see. I'm going to specifically put the division of 2 right there. All right, again, bear with me. you're going to hopefully be able to figure this out. Okay, looking at the picture, delta R. Delta R means the change of R. So that thickness that you have right here, that thickness right there is delta R. It's the change of the radii. Well, I actually have something here that indicates the change of the radii. In my formula, R2 minus R1 is the change of the radii, right? The outside radius minus the inside radius. That's the change of the radii. So delta R is going to be the same as R2 minus R1. And the other piece that I'm going to deal with is the fact that R2 plus R1 over 2, well, if you add 2 radii and divide it by 2, doesn't that just give you an average, right? Add 2 things up, divide it by 2, it gives you an average. Well, here's the piece of information that's important. If I have that thickness become really, 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 really small, so the thickness is becoming very, very, very thin, just like when we dealt with dx, just like when we dealt with dy and stuff like that in AB and BC, we're going to let the thickness of that shell become really super thin. If that's the case, and that the difference between the two R's is really, 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 really tiny, if that's the case, then the average of those two R's is really going to be called just R. So that's the average of the radii, and we're going to rename that R, because the delta R, excuse me, is going to become so thin that the average is basically going to be exactly the same thing as a single radius. Putting all of this together, what we end up with is the volume equals 2 pi R, and that's from that piece right there, H delta R. And the delta R comes from right there. 2 pi RH delta R. All right, now let's pick out a couple of things that hopefully you remember. 2 pi R. What does 2 pi R represent typically? 2 pi R is the circumference of a circle. We're talking about a cylinder here, which is round, so it's going to have a circumference. So the 2 pi R part, is really just the circumference. H, of course, is just going to be the height. And delta R, the change in R, is, again, take a look at the drawing here. Delta R is the thickness of the shell. And we want that thickness to be extremely thin. So we can find the volume of a cylindrical shell by doing the circumference of the shell times the height of the shell times the thickness of the shell. And if we took the shape that we did above and we rotated it around the y-axis, it's going to give a solid that looks like the shape that you see below there, with that hole, the hole kind of in the center. It would look something like that. Okay, so you might ask yourself, well, wait a minute. That thing on the bottom does not look like one single shell. As a matter of fact, it looks like you have one cylinder cut out of the center, and that's true. The idea, which we're going to get to on the next page, is that I'm going to take that shape that we have there, and I'm going to go ahead and I'm going to actually take an infinite number of shells. So I'm going to start stacking these shells up. So Let me see if I can kind of sketch this. You can kind of see it here in this first drawing, but the idea is if I have a shell which is really thin, see how good I can do this. All right, so there's a cylinder. It is supposed to be a hollow cylinder. Well, then if I take another cylinder and I put it in the middle of the first cylinder, basically so that it fits perfectly on the inside, take another shell, line it on the inside like that, and then I were to take another shell, maybe the shell now is a little bit taller, but it still fits. It's almost like when you're a kid and you start playing with those stacking cups. Kind of the same idea there, where the stacking cups fit inside each other. And then I'm going to take the red cup, which is really tall, and it fits just inside the blue cup. There, you kind of get the idea. And eventually, what you'll have is something that actually creates some kind of a curve, whatever this curve happens to be. So that's exactly what we're doing here. We're taking, here's the first cup, here's the second cup, the third cup, the fourth cup. The only difference is these things you can actually, they're over exaggerating the thickness of them. So you can actually see the thickness which is here, the thickness which is here, thickness which is here, thickness which is here, and so on. They're over exaggerating the thickness so that you can actually see what's happening. The idea is once that thickness becomes super, super thin, this right here starts to form exactly that curve. So it's going to take the shape of the solid if we let that thickness again become super, super thin. Again, this is very much like the idea of the infinite number of rectangles when we start to do area beneath a curve. Take an infinite number of rectangles with a width that is so very small you can't even tell that there's a width there, and it fits the curve exactly, which is how we find the area beneath a curve. All right, so that's the general idea of what we're talking about. So obviously what we want to do is we want to take all those shells that we're going to create and we want to add them up. And if you remember back to that idea again of the rectangles, if we're going to add them up, we're going to integrate. So we're going to integrate from A to B, and if you kind of look up here, it's A to B is going to go from the center part of the first part of the shell. So we're not actually going to go from here because the shell doesn't actually start there. It's hollowed out. The shell starts right there. So we're going to go from A out to B, which is the end of where the volume is going to be. A to B of 2 pi r. But r, in this case, because the radius actually goes always from the center, or the axis of revolution, out to the edge, well, the edge, in this case, while it does hit the function, remember this is y equals f of x, this is just an x value. Okay, the radius is always just an x value. B is an x value. Whatever that's associated with is an x value. Whatever that's associated with is an x value. If I did the next one, whatever that's associated with is an x value. So the radius, in this case, when you revolve around the y-axis or something around a vertical axis, will always be in terms of x. In this case, because it goes from the y-axis out to an x value, it's just x. So there's your 2 pi r. The radius is x. In this in particular case, the radius is x. The height, because now that's the circumference, now I need to do the height. The height in this case is just f of x, right? The height is f of x, the height is f of x, the height is f of x. Just depends on where it is, but the height is always going to be f of x. And then the thickness is that change in r. Well, remember, r is x, so the change of r is the same thing as the change of x, delta x, or in terms of integration, dx. Okay, another way to visualize this, if you're not able to see it in the way we just did it, is to take one of those shells, and so the idea is if you take a shell, and I was to go ahead and slice the shell, like right here, just literally cut it right there, and open this thing up, if I could spread it out, it's going to look like this right here. And this is nothing more than a rectangular prism. And how do we find the volume of a rectangular prism? Length times width times height. The length is 2 pi x, because again, the length of this prism is basically the circumference of that circle. If we folded it back together again and made a circle, it would just be the circumference. The width is delta x, and the height is f of x. So, once again, integral a to b, the 2 pi x part, that's the circumference, times f of x, that's the height, oops, times dx, which is the thickness, or the width. So, in general, this is going to be our equation. Now, if you had something where it was revolved around the x-axis and you needed to use shells, the only things that are going to change is this is going to be 2 pi y, and it's going to be some function of y, and dy would be your thickness. So it'll just be turned on its side. But it's the same exact idea. All right, I think what we're going to do is we're going to stop this video here, and then we're going to come back with a second video to keep them a little bit shorter, and the second video will be all the example problems.